Hello everyone, thank you for joining this presentation. Today I'm going to talk about the implications of pavement life cycle in the total GHG emissions of the US nation. I will also discuss the role of possible solutions to mitigate these GHG emissions from a life cycle standpoint. To start this presentation, I would like to share a part of the American job plan proposed by President Biden that intends to spend more than $100 billion to improve the US road network. The sustainability of road infrastructure systems is one of the criteria that is targeted in this proposal. While this increase in the budget can provide a potential to reduce the climate change impact of the road network, it's very important for us to know the extent to which that can be achieved in different pavement life cycle stages. In fact, pavement can contribute to the nation's GHG emissions throughout its life cycle, rather than the embodied impact reductions related to the construction materials. We can think about how to manage and build pavements to reduce the use and end-of-life environmental impacts. For example, by making pavements more reflective, we can have GHG savings, or maintenance and repair actions can make the pavement surface smoother, therefore less fuel consumptions induced by the pavement surface characteristics. And at the end of life, we can use the recycled content to minimize the primary materials production. Therefore, we decided to investigate the role of life cycle environmental performance of the US pavement in mitigating the GHG emissions. And for this purpose, we defined and developed a bottom-up approach to investigate the environmental impacts of the pavement life cycle for each individual road segment. So as you can see on this screen, this approach comprises a nationwide analysis. We collected the data related to the pavement statistics in each state, and then we contextualized the input in the network level, including the climate conditions, the local maintenance and repair actions, and materials used for pavement rehabilitations. And with the individual assessments of the segments, we incorporated life cycle assessments to quantify the environmental impacts of the road network. And with regional aggregation and nationwide aggregation, we could achieve the total life cycle GHG emissions of the road network in the United States. So here I would like to show you the nationwide results of the total life cycle GHG emissions of the US pavement network. On the y-axis, you can see the annual GHG emissions in terms of million tons CO2 equivalent, and on the x-axis, you can see the year starting from the embodied impacts related to the new construction, maintenance, and repair actions on the road. We can see that the embodied impact is around 20 million metric tons CO2. The deflection-induced fuel consumptions is very similar to the embodied impact, while the roughness-induced fuel consumptions is twice bigger than the embodied and excess fuel consumptions, implying the importance of the use phase incorporations in the pavement life cycle assessment and in the decision-making for pavement decarbonization. The albedo effect, which includes the reflectivity of the pavement, was also around 20 million metric tons per year. And if we sum up all these values, we can see that the total life cycle GHG emissions of the pavement network in the United States is around 90 to 100 million tons CO2 per year. The other important observation from this result is that compared to the 2016 level emissions, we can see a decreasing trend, and then we see that the trend is going to be increasing in the future after a while. And this is because the vehicle fuel efficiency and partial replacements of the virgin materials with byproducts can reduce the GHG emissions of the nation in the future, but the demand increase and the traffic volume increase will dominate the other factors. Therefore, after 2038, we can expect an increase in the total GHG emissions of the pavement life cycle. And it implies us that we need to take an actions to reduce these GHG emissions. To reduce the GHG emissions of the pavement life cycle in the future, we propose 6 different ambitious actions. These ambitious actions include achieving net zero GHG mixtures, both for asphalt concrete by 2050, which would reduce the materials production and construction GHG emissions. We can have concrete overlay actions added to the maintenance and repair actions of the DOTs and municipalities. So we can have some benefits in the use phase in terms of the GHG emissions, but we may have some extra GHG emissions and burdens for materials production and construction. We can have an extension for the end of life carbonation, meaning that we are leaving the stockpiled demolished concrete for a longer period of time, so we have more carbon dioxide absorbed from the atmosphere. We can have an increase in the budget, which will give us a smoother road surface. We have less excess fuel consumptions induced by the roughness, but we have to spend more materials and construction equipment to provide that level of smoothness. The increasing in the stiffness can reduce the deflection, excess fuel consumptions, but materials production and construction should have some environmental burdens. And finally, increasing the surface reflectivity using reflective materials can effectively reduce the environmental impacts of the pavement during its use, but we may need to have some materials for using this pavement and making that pavement more reflective. Here's the cumulative GHG emissions of the pavement network from 2017 until 2050, under two scenarios of no change, the first column, and ambitious scenarios, the last column. Under the no change scenario, we assume that there is no improvement in the environmental impacts of the pavement life cycle. Therefore, under these scenarios, we observe that 30% of the total life cycle GHG emissions come from the embodied impact, and the rest of them is attributed to the use phase. After the implementations of the ambitious actions, the dark purple color bars, in addition to the projected actions that are already included in the policies of the nation, the light purple color, we can see that 50% reduction is expected by 2050 under the ambitious scenario. And only 16% of the total life cycle emissions is attributed to the embodied impact. This amount of reduction is equivalent to 5% of the total road transportation emissions in the US during the same period of time. And as you know, the road transportation is the largest contributor to the GHG emissions of the nation. Therefore, reducing these emissions by 5% only by pavement is a big contribution from civil engineering community. You can also see the pavement GHG abatement cost on this graph in terms of dollar per ton CO2 on the y-axis, and on the x-axis is the cumulative GHG savings that we could expect during this period of time. On the left part of this chart, you can see the embodied impact attributes, including low carbon binder, reclaimed asphalt, and binder intensity, that simultaneously reduce the environmental impacts and cost of the pavement life cycle, while other attributes more related to the use phase, such as reflectivity and fuel efficiency, will have a higher cost, but we have more extensive reduction expected from these attributes. So to conclude this study, based on our analysis, we found that in the near term, we have a reduction in the environmental impacts of the total pavement life cycle, but there is an increasing trend in the medium term. Therefore, we need to take an action to reduce this environmental impacts. Then the contribution of pavement embodied impacts is around 30% of the total life cycle GHG emissions under the no change scenarios, implying the importance of simultaneously considering the embodied and use phase impact. The embodied solutions have the lowest abatement cost. Therefore, we need to prioritize these solutions in the short term, while the use phase solutions have larger saving potential. The improvement in the technologies will help us reduce the abatement cost for the use phase, and therefore we can have more flexibility to reduce the environmental impacts. And at the end, the proposed scenarios could offset 5% of the total road transportation GHG emissions, which is the major driver of GHG emissions in the United States. With that, I would like to thank you for joining this presentation.